Okay, people can see the screen, right?
Yes.
Okay. So today we're going to talk about a new problem. Sorry for being disorganized today. Okay, so most people would have seen what is called as a traveling salesman problem. Has everybody heard about this?
Yes.
Okay, so now we're going to look at a online version of a traveling salesman problem. So this itself is a challenge, that how do you exactly model this? So it's not obvious how to model this. So there are multiple versions. We'll look at version number 1. Version number 2 ends up being slightly more difficult. Okay. So think of, you're given a metric space. If you want to not worry about it, just think of R2. And we have a distance measure D. All right. Now, a set of 10 requests are going to arrive. Request I arrives at time Ti and location Li belonging to M. All right. So each request I is a tuple. Li, comma Ti. Starting point is, without loss of generality, we're going to take the origin. Now this is the time element, which is important. Speed of a walker is going to be 1 or unit speed, 1 unit per whatever time unit you want. All right. So what do you have to do? So you're starting from the origin. So let's say the first request arrives L1 T1. So you're allowed to, so time also starts from 0. So you're starting from the origin, you're allowed to wander off anywhere you like. The speed at which you can move is 1. All right. You are required to visit all the locations that are part of the request set. So L1 T1, L2 T2, so on, blah 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 until Ln Tn. Okay. And you have to end up here, end up at the origin. One condition, you can visit a request only after it has been revealed. You can visit a request only after it has been revealed. You could have possibly already touched that location before, but that is not going to be counted. Unless that location is actually revealed, we will not count that request has been fulfilled. You can think of it in terms of fulfilling a request or not. Is the problem description clear? We are not defined yet what the cost is. So I'm soon going to define the cost, but is the
Yes.
request okay? So now, cost of an algorithm is the total time it takes to return to the origin while fulfilling all requests. Does this make sense?
Yeah, since speed is 1, so it is equivalent to distance only.
See, it's a weird version of traveling salesman. It's not the usual version where you're given a graph and you're allowed to travel. Here, what is happening is your starting point is 0, the origin. Now, the first request is revealed L1 T1. You may or may not go straight. You can wait. That's up to you. You can wait for L2 T2 to appear and then figure out whether it's better to go first to L2 before you go to L1 or so on and so forth. All I'm going to count is the total time you take to come back to the origin after fulfilling all the requests. And a request can be fulfilled only after visiting that location after it has been revealed. Make sense?
There should be a restriction also, right?
Which restriction?
On how many requests we can wait. Otherwise, you would
How many?
wait.
Sorry, say it again.
Let's say you are revealing total number of points are n.
Yes.
Okay, you may decide to wait up till n points, right? Then it will become opt. I mean,
So I will never tell you what n is, right? Ahead of time, nobody knows what n is.
okay,
You don't start, you don't start. OPT might have started. And if you don't start, you can easily destroy the algorithm, right? Suppose this is only one request which is going to show up and you didn't start. OPT would quickly go and come back and you are just still standing at the origin. So n is not known ahead of time.
okay. So that waiting time is also counted in the cost.
Yes. So
Okay,
absolute time starts at 0. You can think of it that way. And the end time is when you return to 0 after fulfilling all the requests. Make sense? Any more questions on the model? This is one way of formulating it. There are many other ways of formulating online TSP. But this is kind of nice and neat. And what we are going to see today is everything can be explained in pictures. Any other questions on the model or the cost? It's a good time to ask clarification questions.
If n is not known, so if my algorithm reaches like at a point, and suppose no more points are coming, then it will wait forever, right? I mean, how it will know that if it has ended or something?
That's up to you. You can go back to the origin,
Okay.
right? You can decide an algorithm which waits for a while. If it doesn't see any more requests, goes back to the origin. He can restart if he wants. No problem. He can restart. So it's not that origin has to be touched only once. You can keep visiting the origin again and again and again, as many times as you want. Does that answer your question?
Yes.
Sorry?
so in TSP we visit exactly once, right?
Right. So here there is no such restriction because I have not told you what are these L1s and T1s are.
Okay.
So the algorithm which you're ever also going to think about, you keep revisiting origin multiple times. So that's not a restriction. You can visit wherever you want to go, you want to go. All we care about is you should return to origin, and that's the time I'm going to count after fulfilling all the requests.
Okay, we have to visit all the points and come back to origin.
And
That's the only condition.
And a visit is a legit visit only after you visit it once it has been revealed.
Right.
So that's important. Okay, so mu A as usual is nothing but max over input CA over CO. So, but I'm not going to belabor what a metric space means. So, the definition for any path P belonging to M, let mod P be its length. So, for example, if P was x1, x2, xn in order, mod P means summation I going from 1 through n minus 1 dxi xi plus. All right. Okay, so now let's look at the lower bound. Give me a quick lower bound when m is just a real line. This is easy. So we have this real line. This is our starting point. Give me a small input and try to show a lower bound of 3 by 2. That your algorithm is going to take 3 by 2 fraction more time compared to the OPT. It's very simple. So keep it very simple. All you have to give me is the input. L1, T1, L2, T2, or whatever you need. Let's see, 1, 2, 3, that's 1, that's 2. You're still connected, right?
Yes.
Oh,
OPT can visit in any order, right?
OPT can do whatever, right?
Wait, OPT also has to wait for them to be revealed, or it can visit them anytime it likes?
No. The same restrictions remain for every algorithm. A request is defined to be fulfilled only if you visit after it has been revealed. Otherwise, I think you can make the competitive ratio infinity. The OPT just goes simply, touches all of them and comes back at whatever time, and then the request is revealed. So the algorithm is just waiting. So that's not fair. Think of the simplest input you can think of. How do you fool an algorithm? So tell me some value for L1 and T1. Let's say T1 is 1 and L1 is +1 or -1. Now can you tell me how to go ahead? What will the OPT do? OPT will know what exactly L1 is, while the input can be either +1 or -1.
Okay, so OPT will start moving at time 0 itself and
Correct. So
come
that is
back
allowed.
by time 2.
Correct. So say L1 is +1. Then OPT starts at time 0. That's allowed. Visits L1 at time T1, which is exactly its time of revelation. So that's allowed. And comes back to O at time T equal to 2. So his total time taken is just 2. Now tell me, what does an online algorithm do? See, online algorithm could also predict something. So if it predicts that, or let's say the location of LAT is greater than 0, then I give L1 is equal to -1. Otherwise, if LAT is less than equal to 0, L1 is equal to +1. In both cases, how much is the time taken by the algorithm to come back to origin?
At least 3.
Exactly. So CA is greater than equal to 3. Is everybody with me? Why I can do this? I can choose,
Yes.
depending on what the location of the algorithm is, what I am trying to do. The OPT, irrespective of it's +1 or -1, can make sure that its cost is 2. So cost of algorithm A is surely greater than 3. So therefore, mu A is greater than equal to 3 by 2, just by looking at a very simple metric space. Now we'll go to something more stronger, that mu A for any, or other, let's write this, greater than 2 minus epsilon for any A for a choice of M. For each M, you might get a different answer for the competitive ratio or the lower bound. What we are saying is there exists a metric space for which any algorithm A, for the moment deterministic, has competitive ratio greater than 2 minus an epsilon. But once I make the picture, proof should be clear. So to make sure, should look like a square. Okay, so think about this boundary as your metric space of the unit square. Only the boundary. The inside is not contained. Okay. So bound M, just the boundary of the unit square. And let's say A, B, C, D, and this distance, let it be some delta. Essentially, delta will be 1 by n, where we will choose n later. Now, can you tell me how to choose an input such that any algorithm will be fooled? It's not too hard. And you want to get to a competitive ratio of 2 minus n epsilon. The hard part has been done. So remember, this is 1. So this just before 1 is n minus 1 such points. Just to represent, this is n minus 1 times delta. So now can you think of an input which will fool any algorithm? Which only lies on the boundary of the unit square. And you can think
So
of,
C is revealed at time 0 and either B or D is revealed at time 1.
sorry, C is, say it again.
C is revealed at time 0 and
Time
either
0
B
itself.
or D, yeah, and either B or D is revealed at time 1. No, actually, wait, that does not.
No, it's okay.
Yeah.
It doesn't go to 2, it's okay. But at least
Yeah.
let's see what happens. So suppose C is revealed at time 0. What will OPT do for this input? Will it start crawling or it will wait for B or D to be revealed?
It will start traveling towards whichever one is actually revealed.
Okay, so let's say OPT. See, OPT knows the input. So let's say C comma B is the input without loss.
So does algorithm and OPT start from the same position at the
Yes,
beginning?
yeah. I said that original starting point. So A is origin.
Okay. A is origin. Okay.
Otherwise, things can be completely different. So let's say input is C comma B. C is revealed at time 0, B is revealed at time 1. Let's just make it more precise. C comma 0 and B comma 1. Okay, so what will OPT do? Will start walking A to B, B to C, and can come back however it wants. It doesn't matter, right? B to A. And fulfills all requests. Is everybody clear in this?
Yeah.
Yes.
Okay, so what's the cost of
Yes.
OPT?
4.
Four.
COPT is 4. Now tell me, what should the algorithm do? It doesn't know it's B or D, right? So suppose it doesn't start, let's say it starts at time 0, so that we don't have to. Suppose an algorithm starts to follow a path A, B, C. Okay, so at B itself, it knows that B has been revealed or D has been revealed. So what should I do? So suppose it has taken this path A, B, C, and at this point, either B or D is revealed. Which one should I reveal first of all?
D.
D for Delhi or B for Bombay?
Delhi.
Delhi, okay. So suppose D is also revealed. Then what happens? It keeps going towards C. Then it touches D and it comes back. Right? But its cost is also 4. So it did not fool it. What if it was B instead of this?
Then also 4.
Then also 4. So
You
this
should
input is not.
reveal, you should reveal B or D at time 3.
Okay, very good. Let's try that. But the OPT's cost will also change, okay? Will it not?
No, it will
No,
be
it will
the
not.
same.
Yeah, that's right.
It will not change.
It will not change. So let's say, yeah. So this still works, right? Because it knows what's coming. So it goes to C and comes back to B at exactly time 3 and goes back. So it's 4. Now let's look at what A does. So until time 2, it has gone to C and it has no extra information. Now it starts following either this path or it goes to B towards A, either of the two. Now, depending on what it does, if suppose it follows this path, you give B as the input. At time 3, in which case what will happen? You'll go A, B, C. You have reached D at time 3. B is revealed. Now it's your choice. Do you want to go to C, B, A or D, A, B, A? Both of them are going to give the same cost.
Same. Yeah.
So how much is the total cost?
6.
6. So CA is 6. So we are back to 3 by 2. We want to go towards 2. So you'll have to do something more with this. I think you're catching the idea now, but it was good to do this exercise. So let me give you the precise input which gives 2. Okay. See, you should have noticed that I gave you this delta which you're not exploited yet, right? So you should have, that hint would have been interesting. So do people want to think about how to use delta? So currently we're not used delta. We only looked at the corner points and done everything. So let me define. You can keep thinking what you want to. I'm just going to define something.
If you go n-1 delta ahead, then reveal that point. Is it like that?
No. It's slightly more, but keep thinking. I'm just going to write something in the meantime. So these are nothing but these points. I'm just defining them as A to B as these n points sitting on the x-axis. That's all I'm defining. This point, this point, this point, all the way to B. All right. Similarly, as B to C is this set of points, C to D is this set of points, and D to A is this set of points. So I'm going to use those points. So that how many points I've got? 4 n points. So input at time 0 is S A to B. 1 point essentially each of these guys. 4 n plus 1 points. One each for each of these over here. Valid input, right? Is the input clear?
So you ask for
All these point at time
n
0.
plus 1 points.
4 times n plus 1.
Yeah, okay.
And that all of them in ask for time 0. Now you decide how you want to travel. Okay. So without loss, we can assume that any A will follow some trajectory, right? So let's say A, B, C, D, A. That's one trajectory. If you alternate between this wall and come down and do something, it will only pay more cost. So if you have started going around, because all of this information is revealed at time 0, the algorithm is aware. So either it goes A, B, C, D, A or A, D, C, B, A. There are only two reasonable trajectories. Okay, so now what is the cost of this algorithm? Now, given that I'm following this is an optimal path, right? I need to input something more for me to trouble this algorithm. What should be that input? Look at this. It is following this path. So now build upon what you just did in this smaller example here to make it pay even more. See, it has chosen this path. You can use that information to give me the input. Because
So it
after it has
only
crossed this, yeah, after it has crossed certain requests, it's not expecting them to come back again. Go on. Yashan?
is it like diagonally opposite kind of?
It's not that complicated. I'm giving you the hint that following this path, it is expecting that the points that is already fulfilled, they're not going to come again because otherwise it has to keep going back and further and further. So what kind of points are troublesome points for it? Which it has just fulfilled. So let me just draw this again. So what is the location of A at time 2 minus 1 by n? At time. Remember this following this path. A, B, C.
Just
box
before reaching C.
So somewhere here. This is my LA T, where T is T equal to 2 minus 1 by n. Now, what kind of input can I give at time 2 minus 1 by n and make A pay a very large cost? So suppose at this point I ask for S A to B and S B to C. That is 2n plus 1 requests at time 2 minus 1 by n. Now this algorithm is in trouble. It has reached here. It wants to go towards C, but these requests are now revealed. What should it do? Either it can keep going and then, but it has to come back all the way to the top, or it can backtrack here itself and reach A and then possibly go to D, go to C and come back. Is this point clear? So its algorithm currently is at this particular location at time t is equal to 2 minus 1 by n. All these points are requested at this point and they have to be fulfilled. What are the options algorithm A has? Either it goes back to A, then goes up, goes to C, and then follows whatever path to come back to the origin. That's one way. Or it keeps going on its current path, reaches A, goes up, and then again comes back however it wants to come back. In both these cases, what is the cost of the algorithm?
8 most.
This part is getting repeated twice, right?
Yes. So
A,
how much will be
B,
the
B
cost?
to C.
Eight minus 1 by.
Does everybody get this? Is that correct? Why should it be 8? See, at time 2 minus 1 by n, I am here. Now what do I have to do? I have to go, let's take this option, and I have to go back to A. So I spend another 2 units of time. And then another 4 to complete another tour of this. So 2 by n is because I'm just right before it. So that's why an extra 1 by n gets counted. But everybody sees why 8 minus 1 by n shows up. 1 by n is extra for we are just below point C before we restarting. Agnew, is this okay? Why 8 shows up?
Yeah.
All right. So now what is the cost of OPT on the same input? OPT just knows that these are coming. So it just starts going this way and finishes in 4 units of time. Make sense? Everybody with me? So mu A is at least 8 minus 2 by n over 4, which is essentially 2 minus epsilon for any epsilon greater than 0 by choosing n large. So as I said, everything is pictures today. Are we happy of what we did? Yashwant, is this clear? Agnew, Somajit.
Yeah.
All right.
So,
Yeah.
so this 2 by n came because that part, right? That last
Just
part,
here,
just
that
before C.
we stopped right before time 2 minus 1 by n. So that extra 1 by n has to be traveled, which I did not
Right,
travel. I started to walk back.
right.
That's all.
Yeah.
So on my onward journey, I 2 minus 1 by n. On a backward journey also, I only took 2 minus 1 by n. And then I did another 4. That's all.
Yeah, right.
Okay, so now algorithm. Who wants to have a crack at it? What algorithm will you prescribe? Any candidate algorithm comes to mind. You'll be surprised. The algorithm is going to be very simple and the analysis is even simpler. So no non-triviality today. But yeah, and we have plenty of time. So do think about the algorithm first. What algorithm comes to mind? At any point of time t, what you know is all the unfulfilled request and your current location. And your objective is to complete all the unfulfilled requests and come back to the origin in as little time as possible. That's what you care. And if you want, let me give you for the moment that n is known to you. It's not going to change anything, but if you want, you can take it.
Among the requests that are currently known, find the shortest path, which goes through all of the requests and then ends up back at the origin.
And suppose in somewhere in the middle, a new request arrives. What do you do?
Then you recompute and follow the new path
From that starting point?
from wherever you are.
Yeah. So algorithm is essentially a greedy. So what Larry is suggesting is the following. So current location. So let's say at time t, algorithm is LAT. Let the set of unfulfilled requests be u of t. So you are somewhere here. There are a bunch of these we are not covered yet. This is your origin. So consider these guys. This is anyway. Okay, that's not a good idea to draw this. So these are, let's say, u1, u2, u3. So little ui's belong to the set of unfulfilled requests so far. So somehow find a path which goes back to the origin, connecting all these guys. Okay, that's what you're going to do at time LAT. Now, as time progresses, possibly you're walking along this direction, a new request is revealed. That can happen. So let's say U4 is revealed. Now think about, you forget what you did, you recompute a path possibly which goes from here to here. All right, what is going to happen for such an algorithm? Can somebody say a positive or a negative result for this? That either what the competitive ratio guarantee you can give, or can you give a lower bound on it? So suppose you're following this algorithm, what will be a bad input? And also another question, did on this example, what will this algorithm do? Let's just look at that. So until at time t, at time 0, everything was revealed. So definitely this will be here, right? Either this way or that way. Now all these requests are revealed. What will the algorithm do? Will it match 2 minus epsilon, or will it be larger than that?
It will match up.
Yeah, looks like it will match. So now can people think about any other input for which the competitive ratio will be larger than 2 if you follow this algorithm? Is the algorithm clear to everybody? We will not be analyzing this algorithm. So it's only this is going to be one black box, but we'll have to modify this for our final analysis. But I want to understand, what do people think about this algorithm? Either give a positive result or a negative result, saying here is the competitive ratio, or at least guess what should be, or give a bad input for which this algorithm can be forced to have a larger competitive ratio than 2. And if you can't construct an input, at least talk to me. What kind of input will it be bad? Let's not even worry about constructing one. Why is it not optimal? Let's talk about it. Why is this not an optimal algorithm? Anybody wants to argue there is actually not an optimal algorithm? What is the weakness of it? Let me ask you the same question in a different way. What is the weakness of this algorithm? So think about a new point arrives which is very far. What does it do? See, if no new point arrives, it is locally optimal, right? Because it is finding the best path starting at that current location. So at time t, if no further requests arrive, you cannot improve the algorithm. Algorithm is okay. What if a new request arrives? What could be the bad location of a request which arrives, which will create trouble for this algorithm? So you are here, LAT, and your current path to origin is this, on which you have embarked. And now a new request arrives. Where do you think will be a problem? See, think about it. Let's suppose this is where the newest request is. What will it try to do? It will take all these guys into account and go back to 0. But should this point be even considered for this current tour? Can I not worry about it later? So I'm starting at LAT. If this point was not there, I would have followed this path. Now suddenly this point pops up and now I'm recomputing the path, which is possibly this path. Is there a reason to not do this?
It might be better to.
I got only half of it. It might be better to. I just got that part.
No, I thought it might be better to just continue on that and then go back to the origin and then later go to this new point.
Okay, and suppose you do that, what are you saving?
But I mean, if any more new points are revealed, then you can take those into account.
Yeah, so if you follow this algorithm, you can essentially construct a request sequence where it takes you farther and farther away from an optimal tour. Do people follow this? So the first point arrives, let's say xi is at this extra new point. Okay, first x1 arrives, then x2 arrives here somewhere. Now, because x1 arrived, until x2 arrived, you traveled somewhere else. You changed your path and went somewhere. Now, given that x2 has arrived, you will recompute the path which involves x2, x1, and all the other remaining full. So this process can essentially completely destroy you by increasing the number of these points which keep coming up, they could also go in arbitrary directions. Are people catching the intuition that why it's a bad idea to keep recomputing this path and follow unnecessarily, or you essentially overfitting your algorithm to the input which is coming in?
Are we recomputing or the place where we are currently, from that place we are finding the shortest?
Yes, so that's what recomputing means, right? See, what happened was, supposing only this much input was available. I am following this path, correct? So let's erase this U4 here. Now, before X1 arrives here, sorry, before X1 arrives over this location, I travel, right? I travel on this path. If I had known X1 was coming, possibly that path was not the right path. So I'm unnecessarily making increments in wrong directions. And that is what can be done for every single step. So as soon as X1 arrives, I am unnecessarily traveling during the time difference between when I compute the path and the time at which X1 shows up. Now at time X1 shows up, I recompute my path. Now there's a time difference between when X2 shows up. So in between, I will travel somewhere else. Is this point clear?
Yeah, yeah.
So that is where this algorithm can be forced to commit to much longer path than before. But now can you offer a fix to this? This is not too bad. You just need to fix it. That if a new point arrives, you don't always recompute a path. So what could be a condition under which you recompute a path, or you forget about it and just go back to zero, and from zero you will look back at all the points later on.
So the path including x1, if it is less than or equal to, not less than, say,
Condition. Just tell me precisely. So you are at LAT, unfulfilled request at t minus is u of t minus, and x arrives, x1 arrives at time t. Everything is correct, right? Now can you tell me what should I do? You had some suggestion that take the union of ut minus union x1 and do something.
uh, yeah, and if we defer considering x1 later, I mean,
No, so you have to tell me some algorithm, right?
uh,
When should I
no,
include and when should I defer?
we have to compute the distance of x from the origin.
Okay, you're given that. So d of o comma x1 is known. D comma everything else also is known. So for example, d of sorry.
So d of ut minus 1.
No, d of ut is not well defined. Ut is a path. I can define distance between two fixed points. Ut is a path. Sorry, ut
So
is a set
yeah,
of
it is.
points.
Yeah,
Ut is a set of points.
summation of
Okay, summation of d, or let's say I actually defined something, right? So let's mod u of t. That is the path. That's exactly what distance between consecutive points of u of t is. Okay, so we have this,
minimum of this.
but you have to include LAT also in this, because I am currently at LAT. The set of unfulfilled points is UT. So this is my current location. Okay, here let's say this is my current location. U1, U2, and U3 are yet to be visited. Now tell me for this example, what should I do? And a new point x1 arrives. Just tell me for this example.
UT minus LAT is what you have already computed.
No, no, LAT, this is a location standing. This is not a distance. These are locations. LAT is a location, U1 is a location, U2 is a location, U3 is a location. So are you saying add this distance plus this distance plus this distance? So this is the total path length on the path I am currently on. Now if I include x1, it might completely change.
Yeah, you compute the length of the path starting from LAT to origin, including not including x1,
Okay,
uh,
that's one answer.
plus the distance of x1 from the origin.
Okay,
Okay,
you
that
should
is one
count.
of the arguments in the
No, no,
min.
you should count twice, right? If x1 is the new
Twice,
point.
twice. Yeah, twice.
Okay, fine.
Comma, the path from LAT to
No,
origin,
no,
including x1.
right. So that's one way of making it choose the better of the two options. So
Yes.
that's one way of doing it. We'll do something very simple. So the algorithm is as before. So it's called algorithm is called plan at home. It's not the name I gave. This is what is now. So essentially, it wants to revisit origin often enough. So that's what home is. If the walker or the algorithm is at the origin, follow an optimal path considering all the revealed requests that have not been fulfilled. So this is, if you go and hit an origin at any point of time, this is what you should do. 2. Now what happens if you are actually traveling on one of such paths? So let LAT equal to C. Okay. This is the time T where your location of the algorithm is LAT. A new request is revealed. At location X. We'll do two things. So this is the counterpart of what you're trying to do. X comma 0 is greater than D of C comma 0. Go back on the shortest path. That is essentially a straight line on a metric space, whatever the shortest path might be. Go back on the shortest path to the origin. So don't worry about fulfilling anybody. Just run towards your origin. B, disregard X or the new request, disregard and carry on the optimal path you are on. The algorithm is carry on the optimal path currently started. No, currently started. Since the previous visit to the origin. So it is simpler than what you're suggesting. What is it saying? You are at LAT, okay, and this new point x1 gets revealed. Look at the distance between origin and x1, and look at the distance between origin and LAT. This, in my language, it is C. What do you do? So this is my C, this is my x1. You are currently at C. So if DC0 or D0C is less, you just head back to the origin. And we know once we hit the origin what to do. All right. Otherwise, in case this distance d of 0 comma x, so x is somewhere very close to the origin, not very close, compared to C it is close. Disregard that x even arrived. You just follow whatever path you are going to follow and go back to the origin. And once you hit the origin, follow what you're supposed to follow once you hit the origin. Is the idea clear? Is the algorithm clear?
Yes.
Everybody, is the algorithm clear? Somebody is messaging me. Somebody, you can say, I take some time to go and look at the chat. Yashwant, Agnev, is the algorithm's idea clear?
Yeah.
It's simpler than what you suggested. What you suggested is also fine. The analysis, you can try to do the analysis. I haven't done that analysis for your algorithm, but this will be very simple. Okay, so theorem. Mu PAH is at most 2. So you don't need, so the first thing you should realize is you don't need randomization here. So deterministic algorithm is able to get whatever best you can do. So the idea of the proof is to concentrate on the final request that arrives. At time Tn. Depending on that, we will do all the analysis. Okay. So some notation that the script T, hopefully this is clear, that the script T OPT be the OPT's tour with the least cost. All right. That also has to satisfy the same constraint. Starts at origin, ends at the origin, and visits all locations after they are revealed. So first thing to note, claim is greater than equal to max of Tn, comma, sorry, this is not this. TOPT is just the COPT. This is my total time taken. Okay. Do people agree to this? That the cost of the OPT is at least Tn or max of Tn, comma, the path length of path that OPT follows.
Yeah.
So this is because the last request is revealed at time Tn, and after that you have to come back to the origin. So you could not have finished before Tn. And similarly, because you can walk only at unit speed, you cannot get into time which is lower than the path length of the optimal tour. So this is almost an immediate fact. All right. So now for the PAH, let's look at what happens if at time Tn. So time Tn is what is of importance to us. So let PAH be at the origin at time Tn. So tell me, what is the cost of PAH going to be under this case? So you're standing on the origin. You have a set of unfulfilled requests. Let me call them UN because time is Tn. So it's going to start some optimal tour and come back to the origin. Correct? And let that tour be Tn PH. So can you tell me the cost of PH?
Tn plus length of TNPH is tau NPH.
Is everybody okay? Just immediate. Because I'm starting at time Tn and I'm taking this path and walking at unit speed, this is just obvious. And what can I say about this? I want to compare this with script TOPT. Can I compare this against this? Tn will remain Tn. is this inequality correct or not?
Yeah.
So what's the justification for the question mark? Agni, is this question mark clear why it is true?
Yeah.
Can you give me why? I want a precise one line answer. The claim is that this quantity and this quantity is lower bounded, an upper bound on TNPAH. Why is that?
When PH is a tour of some unfulfilled requests, and it is a subset of all requests.
Mala, I'll come to you. Agni, do you follow this? I want a precise argument. It is like less than 5 words.
Yes, like why OPT is over a bigger.
Exactly. That's enough. Now I got it. I got what I wanted. So UN is a subset of set of all requests. That's all. So I can remove the question mark. So because I've already bounded COPT by max of this quantity, and this is nothing but this is at most 2 times COPT from 1. So if at time Tn, pH happens to be at the origin, I have what I want. So now let's look at the case when it's not at the origin, it's somewhere else. So let pH be at LAT, which is not equal to that. Now case A, see Tn is the time at which the last request is being revealed. So by the definition of my algorithm, the decisions are going to depend on where I am compared to the request. So let's say case A, and C is nothing but LA of T. We just shorter form. So D0XN. So the new request is actually farther away compared to my current location. Let's look at this case. So pictures are again useful. So origin is here, XN is here, C is here. And I have already embarked on some path, and my anticipated time is this, but my algorithm is telling me to just head back, right? So if I do head back, what's the cost I'm going to pay? So what is the cost of PH? So this is my C, this is my XN. Can somebody tell me the cost of PH? See, XN is the last request, so no more requests are going to show up after this. So once I go and hit the origin, I'm going to embark on a final tour, which will cover all the unfulfilled requests. So how much is this?
C plus twice of
C, nahi, D0C.
Tn plus D0C.
So Tn is the current time plus D0C which I travel, and plus the final path I'm going to travel, which I denote by Tn of PAH. So that's my PAH's cost. Now what is OPT's cost? And this also by definition, because this is true, from 2 is at most Tn plus D0XN plus Tn PAH. Correct? Now what is the cost of OPT? At time Tn, Xn has been revealed. So what is the cost of OPT at least?
Tn plus D0XN.
Tn. See, at least you have to go back from here to here. It could be that the OPT was standing here at time Tn. So at least it has to travel distance of 0, Xn since time Tn. So this again, we forgot. We should be able to write this again. D0Xn plus T OPT. The same fact as before. So if you combine 3 and 4, what do you get? CPAH Is at most how much? Can I say it is COPT 2 times?
Yes.
Does anybody have a question mark here, or should I move on?
So can you say this once more?
So we've got this and we have got this. If I combine 3 and 4, do I get this?
Okay.
Everybody happy? So I promised you today will be a very almost elementary analysis and a very strong result. So nothing is non-trivial here. It's just that once you notice things, things are going to be very easy. So now the second case where xn happens to be here, not far away. In which case we will disregard xn. So xn is here, and now C just carries on its path, goes to origin, and then we'll worry about what is xn. So case B. So let at time tn the path which PAH embarked upon, which path PH TTH and TN, the path which PAH is following. TN PH. Now this is an important definition. Let IN be the set of requests that PAH has disregarded since the start of TN PH. Make sense? So XN is automatically part of this set IN, but IN could be much bigger. So just to show pictures, so origin, this is the current path which OPT is expecting to finish. So it could happen that X1 arrived, not, yeah, let's not call it X1. Let's say X30 arrived, which was very close compared to where it was at that point. So it disregarded X30. So this was the location of X30. Then some other time, so T1, T2, let's say X31 arrived, it disregarded X31 and so on. So IN contains all these requests. In particular, definitely contains the last one. All right, definition of IN clear? So IN is not a singleton. It could possibly contain more than one element other than XN. Okay, so now look at set IN and let XF belong to IN be that request which the OPT visits the earliest among requests belonging to IN. Is this definition clear of XF? So we have some set, let's say X30, X45, whatever. Among these, let's say X31 is the location which OPT visits before visiting X30 and X45, and of course XN. So these guys are all in IN. Let the arrival time of XF be TF, which by definition is less than TN. And let PIN star be the shortest path that starts at XF, visits all locations in IN, and ends at the origin. So let me draw this again. So XF is some node. There's some other nodes, 31, 45, XN something, and there is some origin. So what is this? This is some path which touches all these things and reaches. And among all such paths, the path with the shortest length is called P of IN star. Only considers these nodes, doesn't look at anything outside. All right. So this is a standalone quantity. OPT doesn't have to do this. XF is defined with respect to OPT. But PIN star is not defined what OPT is doing. PIN star is a optimal path of the shortest length which starts at XF, covers all other requests belonging to IN and ends at the origin. Now can you give me some bound on COPT in terms of the time at which XF arrives and the length of PIN star? Is the question clear? I want the cost of OPT to be lower bounded as a function of TF
plus
and
length of PIN star.
are you saying this?
Yeah.
Okay, so TF part is clear because TF is the time at which XF arrives. And we are also saying that among the set of these X31, X45, XN, OPT visits XF the first. Why is this term also correct? I actually said it, but I just want somebody to say. Yashwant, do you want to say why this is true? That will make sure that you understand the definition of this. It's all essentially by definition.
We have to prove by contradiction.
No, directly. Why should
The
this
way
be?
we have, this
No.
is the shortest.
No, that's not sufficient, right? OPT need not follow it. You have to argue slightly differently. So what is TF? TF is the time when XF is revealed. That much is clear?
Yes.
Okay. Now what is the definition of XF? Among all nodes of IN or among all requests to IN, requests of that IN consists of, XF is the request which OPT visits the first. So that time cannot be before TF.
Right.
And all these guys are not visited yet because XF is the first visited node. So OPT at least has to, it can also like it might go somewhere else and then come to X45. But what is OPT's remaining requirement to fulfill our objective? That XF is the first location which is visits among these nodes, and all these nodes are not visited yet. So it has to visit this, it has to visit this, it has to visit this. So it at least, the best case in which it could have possibly fulfilled all of the requests, and then it follows this optimal path. So that is why the OPT's cost at least has to be starting from time TF. It at least has to pay so much to get back to the origin. It could possibly go somewhere else and then come back and touch this. Is this clear?
Yeah.
Oh. So now let's look at time TF, which essentially at which time, okay, let me call it this. Remember that XF belongs to IN. That is all the disregarded requests. So at time TF, when XF arrived, PAH disregarded XF. What does it imply? That the current location at time TF, let's call it 0 CF. So XF is less than equal to D0 CF. This is the location of PH at time TA. So this is by definition, because I disregarded it, so it better be that distance of XF from origin was smaller than distance of CF. Okay. Now what can you tell me about how much has PAH covered on the path PNPAH, sorry, on the, it started since the last so I want you to use this, number 5, to tell me at time TF, how much has PAH covered on the path which it has begun since the last time it reached the origin, using 5. At least distance of 0 comma XF,
Yeah.
right? See, the current location is CF from the origin, and XF happens to be here. So this distance, the distance I have traveled is at least D0 XF.
Yeah.
Okay. So how much does PAH need? So therefore, at time TF, the distance remaining, see, distance is same as time because of the unit speed, distance remaining to reach the origin. See, I'm following the script TN path, right? Script TN PAH path is being followed at time TF, and I'm disregarding the new request coming in. So how much is the total distance remaining to get back to the origin? It is
Length
at
of
most
PNPH minus
the length of this path, sorry,
minus
PNPH
distance 0 CF.
minus D0 comma XF. I want XF. CF is true, but I want everything in terms of XF because the OPT's lower bound is in terms of XF. So do people agree to this? That starting from time TF, the distance remaining to reach the origin is at most this much. You can think of this as time, distance or time. So therefore, PAH reaches origin by at most TF plus TNPAH minus D of 0. All right. Now what does it do once it reaches the origin? It embarks. So once PAH reaches the origin, it embarks on the final tour. Let's call that En plus 1 PAH, just to cover all the disregarded requests. Now tell me, how much should this be?
Should be PIN star.
So PIN star is correct. Something more? You have to reach XF, right? See, when defining
Yeah.
PIN,
So
PIN star,
distance from origin to XF.
right? See, what was, just to recollect, what was PIN star? Yeah. All right. So PIN star is the shortest path that starts at XF, visits all locations in IN, and ends at the origin. All right. Now we are saying I am at the origin. What are the set of requests which are remaining? These are exactly IN. These are some set of requests here. Now one of them is at distance of XF from it. And we know from XF, we have said that this much is nothing but PIN star. The best possible path starting from XF, which touches all these nodes of IN and goes back to origin, has at most distance, at most length PIN star. And to reach XF from origin, I just take extra D of 0, XF. So this is by triangle inequality, that I should be able to start my last tour starting from the origin and come back to origin in at most distance so much. So in total, how much have I paid? So what is the cost of PH is at most TF plus TNPH minus D of 0, XF. I'm just using this. That's what we just did. And then we'll plus Tn plus 1 PH. Everybody agrees? I'm just adding 6 and 7. And what do we get? No, I'm not actually. Now I'm going to use 7. So from 6 and from 7. So TF plus TN PAH minus D0 XF plus D0 XF and plus PIN star. So this and this cancels. So I end up getting TF plus PH plus PIN star. And remember, we did few minutes ago that it is at least TF plus PIN star. So combining this with this and knowing that this is always less than equal to TOPT, CPH less than 2 times. And we are done. Questions?